Okay, so hello and welcome again to our video, and in today's video, we would be analyzing T-beams. So in the first place, what is to be a T-beam? So a T-beam is basically a flexural member that is to be letter T in its cross-section. So its definition would be as simple as that. So for example, that this is to be a cross-section of a certain flexural member, and when we say flexural member, it is to be subject to bending, it means that this is to be a T-beam. Okay, so when do we know that we will be designing a certain T-beam? So in the previous lessons that we had for the rectangular sections such as your DRB and your SRB, let's say which is to be this, so of course this is not a T-beam because of course this is rectangular in nature. So in your singly reinforced and doubly reinforced rectangular beams, the appeal here is that if this is to be your flexural member, the slab that will be constructed over it is to be superimposed. So when we say superimposed, in Tagalog, nakapatong lang siya. So with that, guys, so it is to be, well, once again, superimposed. So this is to be the slab on top. And as you can see, they are not to be homogeneous. So there. So this is an example of a rectangular beam with a slab over it, which is to be superimposed. So for T-beams, instead of superimposing our slab, the beams are now to be homogeneous with the beam. So with that, guys, so in Tagalog, in Filipino, isang buhos silang dalawa. So if this is to be your slab and this is to be your beam, they are to be poured at the same time, or the concrete there is to be poured at the same time, thus resulting to a member or a material that is homogeneous in nature. So what that means is that, so when we say homogeneous, dikit-dikit yan throughout. Unlike for your rectangular beam and slab combination, the slab is just superimposed. So in Tagalog, when you say superimposed, nakapatong lang siya. So they do not act as one. Okay, so with that, guys, so this is an image from Wikipedia. So I will just be increasing its size here. So we have here a new term which we call flange. So if you can remember from before, let's say that this is to be your beam. So this is to be your rectangular beam. So the parts of a rectangular beam, of course, is your total depth. And if this is to be the centroid of your steel area, this is now to be your D, or your depth D, or effective D. And you have BW here. So this is to be your BW. So BW stands for this is to be the base of the web. So BW. So saan ba nanggaling yung BW niyan? So this is for you not to get confused between the base of the flange and the base of the web. But what is to be the base of the flange? So in your T-beams, aside from you having your web, so let's say that this is to be your web, the flange is to be this. So once again, this is to be flange. Oops, sorry. This is to be your flange and this is to be your web. Okay, so moving forward, so once again, this is to be the flanges and these are to be the web. And with that, guys, this is now to be your base of the flange, BF. And you also have this BW, which is still the one that we will, the base of the width that we have been, the base of the web that we have been talking about for the past couple of months now. And then, of course, if this is to be your steel area, this is still to be your depth D. And we have a new parameter also, which is to be the thickness of the flange. And the thickness of the flange is to be basically what it says. It is to be, of course, the thickness of the flange. So it is to be this dimension. But take note, guys, that this is only your depth D if you are to be having a positive moment. So if this is once again your, let's say your beam, so let's say that this is to be your beam, which is to be, wait, di ko ma-drawing ng maayos, so one more time. So let's say that this is to be your beam and this is to be its column. So if this is to be the column, this is to be a beam, this is to be a column, just for example. And if this is to be its setup, so of course this is to be a fixed support, this is to be a fixed support, and of course you have your uniformly distributed load here. And if we are to draw its moment diagram, it would now look like this. So its moment diagram would approximately look like this. So somehow like that. And with that, guys, we have a negative moment here, a positive moment here, and a negative moment here. So what this indicates is that for its bending, so for its manner of bending, it would now look like this. So you have a negative bending, you have a positive bending, and you have a negative bending. So once again, guys, this is just an exaggeration for you to see it clearly. So it would be like that. So with that, guys, you have a negative bending here, you have a positive bending here, and a negative bending here. And in this case, so for your positive moment, in this case, the one that is to be subjected with tensile stress is to be the one at the bottom, and the one that is subjected with compressive stress is to be the one on top. So with that, guys, if this is to be the case here, if the one at your bottom part, so let's say that this is to be for your positive moment, for example. So for your positive moment, the one that is to be subjected with tensile stress is to be the one at the middle. So with that, guys, this is now to be your depth D. Because your depth D is to be, your effective depth D is to be the distance from the topmost compression fiber up until the centroid of your tension bars. So take note, guys. But guys, if this is to be subjected with a negative moment, so this is just for an example once again. So this is now to be negative moment. If that is to be the case, it means that if you would be having your steel rebars here, which you should, this is now to be its depth D. Because its compression fibers would now be at the bottom part. So this is now to be for your compression, and this is now to be for your tension. So take note, guys. So that is for your negative moment and for your positive moment. And you actually do not need to memorize this as long as if you know this principle. Okay, so moving forward, guys. So this is a photo in the constructor.org website. So this is to be the initial shape of your T-beam, and if it is to be subjected with bending moments, it would now look like this in exaggeration. And just like what we have been talking about earlier for your, so by the way, wait, I will just erase this. So for the parts, so this are to be the parts, so this is to be your base of the base of the web, and you also have this base of the flange, so this is to be BF. And this is to be the thickness of the flange and thickness of the flange. So there. So and you also have your span length, of course. So ito yung span length natin. So ayan. Okay, so for us to understand our lesson better, let us just have an example. So in this example, guys, we would be determining the design strength of the T-beam. And when we say we would be determining the design strength, we would be determining the value of phi mn. So this is to be for the design strength, and your Mn is just to be your nominal strength. Okay, so take note, guys, that this section here is to be subjected with a positive moment. So positive moment. So what this means is that, of course, the one at the bottom is to be the one that is subjected to tension, and the one on top would be the one that is subjected to compression. And take note, guys, that if it is to be, let's say, a member which would negate negative moment, so negative moment, for example, and you would be having your steel here, your new depth D or effective depth D is to be measured from this point up until this point. And your compression block, so for your compression block would now be located here. But once again, this example is to be a member that is to be resisting a positive moment. So positive moment, what that means, ganito yung setup niya. Okay, like what I have said earlier, that for your T-beams, your T-beams is very similar to the analysis of your rectangular beams. It's just that we would be having this section. Okay, so we have two cases. So take note, we have two cases in determining. So two cases in analyzing. So analyzing T-beams. So guys, if I would be drawing a strain diagram here, a stress diagram, palagi ako nagkakamali doon. So let's say that this is to be your stress diagram. Of course, you would still be having your AS here, So this is to be for the value for your ASFS. And this is now to be the value of your compression block. So compression block. So let's say that this is to be your compression block. And this is now to be equal to, so 0.85 FC prime times the area of the compression concrete. So let's say that that is to be ACC. So di ko alam kung standard yung ACC na term, but let us just call it ACC in our lesson. Okay, so the main difference here is to be the value for your ACC, because if you can remember from the rectangular sections, the value here would be 0.85 FC prime ABW. So take note that your ABW from before, if this is to be your rectangular rectangular beam, so and this is to be your compression block, your ABW here is to be this area. So this is to be BW and this is to be A. But what if your section would now look like this? So it is either that, let's say, your compressive block is to be located here. So just for pretend, if this is now to be your compression block, it means that the value for the area of the compression block is to be A times BF. Well, self-explanatory. That is to be basically the area there. And as for our T-beam, so for example that your value for your A would now be located here. So let's say that this is now to be its compression block. So the value for our, let's say, ACC is to be equal to, so it will be up to you on how you would be solving for this. So it is either that you would be multiplying, so by the way, I will just be copying this to our next slide for us to have more space. So with that, guys, so we have two formulas. So it is either that you will be solving for the area here plus this area. So once again, solve for this area plus this area, or solve for this area plus this area. So it would be up to you once again. So let us try this equation. So let's say we would be getting this plus this. So with that, that is now to be equal to BF, so base of flange, times TF, so BFTF, so base of the flange times thickness of the flange. So that is to be this area already. So eto. Plus this portion. And this portion here is to be equal to, so if this is to be for your value of A, and this is to be for your value of TF, so with that, so plus here, so A minus TF, so A minus TF. So this is now to be this dimension minus, times BW. So this is to be the base of the web, so times BW. So this is one way for you to get the compression area of your concrete. So theoretically speaking, ganyan yan. And if you want to do it the other way around, once again, it is up to you. So on the other formula here is to be, so ACC, so area of the compression concrete, is equal to, so let's try the other possibility, whereas we would now be, whereas we would now be getting the area here, and we will be adding the area of the flanges here. So with that, guys, this is now to be equal to, so BW times A, or ABW. So ABW plus, so what is to be this areas here? So this is basically equal to, so base of the flange minus BW. So if this is to be the base of the flange and this is to be the BW, you would now be remaining with this, of course, dimension. So BF minus BW times your TF. So this is another equation. So the usage of the equation would be up to you kung anong gagamitin nyo. So depending on the problem or depending on what you like. Okay, so with that, guys, let's proceed. Okay, so going back here, nakalimutan ko na sinasabi ko kanina. So we have two cases in analyzing T-beams once again. So the first case is, of course, if your compression block is to be located here. So the one on red, if that is to be your compression block, let's say that the value for your A is to be less than or equal to the value of your TF. So kapag hindi siya lumagpas dito sa area na to, so that is to be case 1. So this is now to be case 1. And with that, guys, you would now be analyzing it as a T-beam. So analyze as a rectangular beam, I should say. So sorry. So as a rectangular beam. Because once again, guys, if you can remember that in USD, we would not be considering the concrete at the compressive side. At the tension side, I should say. I'm sorry, Lutang. So if this is to be the interface or the limit of your reinforcing of your compressive concrete, it means that the one at the bottom, so from here throughout, they are now to be subjected with tensile stress. And in USD, once again, we would not be considering the tensile stress of concrete. So hanggang dyan lang siya. And with that, guys, we would now be analyzing it as a rectangular beam, but our base would be base of the flange. So the second case is that if your A is to be greater than your TF. And with that, guys, we would now analyze. We would now be analyzing it as a T-beam. So in some reviewer books, in the reviewer, they call this as a false T-beam. So false T-beam. So ayan. Okay, so with that, guys, with that being said, so I will just be copying this once again to our next slide. So with that being said, guys, what we would be doing here is for us to check which case it belongs so that we would be knowing how to analyze this. Okay, so for us to do that, what we will be doing is that we will be getting the area of our flanges, so BF times TF, and we would be comparing it with, of course, the required compressive area. So, gawin na lang natin para di sayang oras. Okay, so for the value for your BF times TF, this is to be equal to 800 millimeters times 100 millimeters. And with that, guys, this is to be 80,000. So 80,000 millimeter squared. So millimeter squared. Okay, so this is to be the area of our whole flange. Okay, so now let us check what is to be the value of our compressive area. So compressive area of concrete in terms of our summation of forces horizontal. So if once again this is to be your stress diagram, so we have here once again your 0.85 FC prime and your ASFS. So let's say that this is to be your ASFS, and we will be assuming that it is to be yielding. So let us check later if it would really yield. So with that, guys, so if this is to be your ASFY, and this is to be for your 0.85 FC prime times, let's say, ACC. So this is to be the area of the compressive concrete. So with that, guys, so summation of forces horizontal, then transposing it to wherever you want. So your ASFY is to be equal to 0.85 FC prime ACC. Okay, so actually, guys, we know all of these values except for ACC. So let us just solve for it. So by the way, guys, we would be using 7 pieces of 32mm tension rebars. So with that, our AS is to be equal to, so looking at the calculator to your left, nawawala, calculator, there we go. Okay, so that is to be pi over 4 times 32 squared times 7. So this is to be the area of our concrete, and this is to be 1792 pi. So 1792 pi. And in decimal form, that is to be 5629.73. But I think it is better if you would be using 1792 pi so that we wouldn't be needing to round off anymore. Okay, so moving forward, so that is once again 1792 pi. So 1792 pi times Fy, and that is to be 420. And this is to be equal to, so 0.85 F prime C, and that is to be 28 times ACC. So with that, we can now solve for the value for ACC. So that is now to be equal to 1792 pi times 420 divided by 0.85 times 28. So our value for our ACC is now to be equal to 99348.248 millimeter squared. So this is to be the area of the compressive concrete. So if I would be copying this to our previous slide, so as you can see guys, that the area of your compressive block is to be greater than the area of your flange. So what that means is that this is to be case number 2, whereas we would be analyzing this as a T-beam and not a rectangular beam. So ayun lang naman yun guys. Okay, so with that, we will now solve for the value for our, let's say, our A, which is to be betas of 1C, and ayun. Okay, so let's us just proceed. So where can I continue for a moment? So I will just be copying this once again to, let's say, this slide. So take note that your ACC is to be 99348.248. And take note guys that this flange has an area of 80,000. So that is to be 80,000 already. So we do not know this value. So with that guys, so let's say that for your ACC, so your ACC which is 99348.248 millimeter squared, and this is equal to the area of the flange which is 80,000 millimeter squared plus whatever this area is. And this area is to be equal to base of the web, which is BW, times whatever this dimension is. And that dimension is equal to A, which is to be measured from the topmost compression fiber up until that point, minus our TF. Because once again, we are just solving for this dimension. So A minus TF. So substituting known values, so for our BW, so that is to be equal to 350 times A minus TF, and that is to be 100 mm. So from that guys, we can now solve for A. So the value for our A is to be equal to, so 99348.248 minus 80,000. So 80,000 divided by 350 plus 100. So the value for our A is to be 155.2807 mm. So there. Okay, so confirming, so 80,000 plus 350 times answer, times answer, sorry, minus 100. This is now equal to, so 99348.248. So confirm. So this is to be the value for our A. And if you can remember earlier that we have assumed that our steel will yield. If we have assumed that our steel will yield, we will now be confirming if the steel, of course, will yield. So if you can remember guys that the value for your Fs is to be equal to, so 600 times D minus C divided by C. So let us solve for it using this formula that we have derived before. And the value for your C is to be equal to A divided by betas of 1. And our A, once again, is to be 155.2807. So 155.2807 divided by betas of 1. And our betas of 1 is to be, so betas of 1 is to be 0.85. Since our F prime C is to be 28 megapascal and lower, which is, of course, 28 megapascal. Okay, so with that, 0.85. And our value for C is now to be equal to So 155.2807 divided by 0.85. This is now to be equal to 182.683 millimeters. So substituting all the values here, so our Fs is now to be equal to 600 times what is to be the value for D? That is to be 440 here. So 440. So 440 minus C, that is to be 182.683 divided by 182.683. Okay, so with that, our answer here is to be 845.126 megapascal. So what this means is that it is to be greater than your Fy, which is to be 420. And with such, our assumption is correct, which is of course that our Fs would yield our Fy. So with that, this answer is accurate. Because of course our assumption earlier is correct. Okay, so moving forward, so once again, our main goal here is for us to determine the value of phi mn. So let us solve for mn first. So going back here, since you already know the value for your A, I will just be putting them here. And voila. So for a moment. Okay, so now let us now solve for the value for your nominal moment mn. So for this value, what we will be doing is that we will just be getting the moment about a certain point. And I want that certain point to be this. I want this to be our certain point. And with that, guys, so this is now to be equal to 0.85 FC prime ACC times, of course, your lever arm. So with that, this is to be 0.85 times F prime C. This is to be 28 times ACC. So I forgot what our ACC is. Okay, so that is to be 99348.248. But if you do not want to use that value and you want to solve for it manually here, then let us just do that instead. So that is to be equal to, so just get this total area. So for that area, I want you to solve via TF times BF. So that is to be 800 times 100 plus, so what is to be this area? That is to be equal to BW. So this is to be 350 times A, which is 155.2807 minus TF, so minus 100. So if you would be getting the answer here, that is basically 99348.248. So 0.85 times 28. Sorry, yung area lang pala muna solve natin. So 800 times 100 plus 350 times 155.2807 minus 100. Our answer here is 99348.245. So 99348.245. So for us to have space, since you already know how to solve for that, so 99348.245. Okay, so this is to be the resulting letter C or compressive force C times lever arm. So if you can remember from your rectangular beams before, that for your lever arm, that is to be the total depth D minus A over 2. So tatanong ko sana kayo kung ganito pa rin yung formula natin. Ang problema lang, video nga pala ito. Okay, so short answer, this is not applicable here any longer. Because of course, for this, let's say 0.85 FC prime ACC, the centroid here is not A over 2 any longer. So this is not the centroid any longer because this is not to be a rectangular one. So what we will be doing here is that we will be solving for, let's say, the centroid. So let's say that the centroid is to be Y prime. Sige, Y prime na lang. So Y prime. Okay, so for us to solve for Y prime, let us assume that, for example, so we would be assuming that its centroid is to be located here. So this is to be a rough assumption. So if this is to be, So if this is to be the value for your Y prime, Teka, pangit. Ilipat natin ang location onte. So, for example, that this is to be the location of your Y prime over here. Okay, so for example of your, for your Y prime, so via Varinian's theorem, so Varinian, that is to be, so the total area times Y prime. So we would be using this line as our reference point or our lever arm of sorts. So this is basically the moment of area, no? So with that, this is to be equal to, let's say this is to be your A1. So A1 Y1 plus A2 Y2 plus A3 Y3, etc. But since we only have divided this area into 2, so area 1 Y1 plus area 2 Y2. So that is enough already. So substituting known values for the total area of our compression block, that is once again equal to 99348.245. So copying them here. So 99348.245. So this is now to be our Y prime. Our 80. So for our Y prime, this is to be unknown. And for our A1, so I want my A1 to be the flange or the area of the flange. Erase ko nga lang muna para mas makita nyo. So I want this to be the division line. And I want this to be my A1. And its centroid is to be located here. And for my A2, I want this to be my A2. And its centroid is to be located here. So for A1, that is to be 800 times 100. So that is to be 80,000. Times Y1. So our Y1, so this is to be our Y1. And our Y1, that is to be 100 divided by 2. So 100 divided by 2. And that is basically 50. So that is for our A1, Y1. Plus A2, Y2. So for our A2, that is to be equal to, so that is 350 times, what is to be this value? Once again, that is to be A minus 100. And our A, 155.2807 minus 100, that is to be 55.2807. So 55.2807 times what is to be the lever arm, that is to be, so ano ba tong dimension na to? So 100 mm, because that is to be this. So this is to be 100 mm plus this distance divided by 2, and this distance is to be 55.2807. So 100 plus 55.2807 divided by 2. Teka, ulitin ko yung aking solution. So times 100 plus 55.2807 divided by 2. Okay, so that is for the Varinian's theorem. So I'm sorry, nagkaroon ng angle yung sulat ko. Anyway, so for our value for Y prime, so our centroid via Varinian's theorem is equal to, so 80,000 times 50 plus 350 times 55.2807 times 100 plus 55.2807 divided by 2. So divided by 99348.245. So 99348. So you're checking. So 80,000 times 50 plus 350 times 55.2807 times 100 plus 55.2807 divided by 2. So 9 divided by 99348.245. So our answer here is to be 65.1205 or 1206 millimeters. Okay, so with that, guys, if this is to be your value for your Y prime, it means that from the top portion of your beam up until the centroid, that is to be 65.1206. So with that, guys, so this is now to be your Y prime, the centroid there, and that is to be 65.1206. So 65.1206 millimeters. Okay, so with this, guys, what do you call this? So with that, we will now be substituting it here for us to get the lever arm, because our lever arm should be this distance. So from that point up until ASFY. Okay, so substituting known values here. So for the value for your D, that is to be equal to 440. And the value for your Y, that is to be, of course, 65.1206. So minus 65.1206. Okay. Moving forward, so with that guys, so the value for our MN is now to be equal to, so looking at the calculator, 0.85 times 28, so 0.85 FC prime times ACC, and our ACC is to be equal to 99348.245. So assuming that my calculations are correct, which I think it is, so times 440 minus 65.1206. So guys, disclaimer, if there are any errors here, they are to be in terms of our calculation sa pagpindot lang. And as for the procedure, they are correct guys. But I don't think there is an error here. So 0.85 times 28 times 99348.245 times 440 times 65.1206, and our answer here is to be 88. So 88,639,799.3 Newton millimeter. So if we want to convert this into kilonewton meter, so for it to be converted into kilonewton meter, just multiply this by 10 raised to negative 6 or divide it by 10 raised to 6. So same lang sila. So with that guys, our MN is now to be equal to 886.3979.293 kilonewton meter. Okay, so this is to be for our nominal moment. But once again, the required here is to be the design moment or the design strength. And for the design strength, that should be phi mn. So for the value for our phi mn, so we are only missing the value for your phi. So the question is the value of phi equal to 0.9? So short answer to that, according to our solution earlier, for the value of Fs, hindi. Pero bakit hindi? So why is it not 0.9? Because earlier, when we have solved for the value for your Fs, it is to be equal to 845,126 megapascal. Okay, so if you can remember here guys, if you can remember this graph, so this is for the value for your phi and etc. And let's say that this is to be for your compression controlled region, which is not allowed by the code. Let's say that this is to be your transition zone. And let us say that this is to be for your tension controlled region. So compression, tension, transition. Okay, so anyway, so if you can remember, this is to be 0.65 and this is to be 0.9. And for its limit, so if this is to be the first limit here, so let's say that this is to be the first limit and this is to be the second limit. So the first limit, this is to be equal to, so strain Y. So this is to be for your strain Y. And strain Y is equal to Fy divided by 200,000. Okay, and moving forward, so for this one, this is to be for your strain S, so 0.005. And if you do not want to compare the strain, you can also compare it with the value for your Fs and Fy. So with that, I will just be moving this to the bottom part. And this is now to be the limit for your Fy. And this is now to be the limit for your Fs equal to 1,000 megapascal. And this 1,000 megapascal came from this once again because your strain S is equal to Fs divided by 200,000. And if you would be solving for Fs, given that strain S is equal to 0.005, your answer would now be equal to 1,000 megapascal. And earlier when we were solving for the value for your Fs is to be equal to 845.126. So with that, guys, the location here should be at this point. So approximately here. So this is to be, once again, 845.126. So 845.126. And what we are solving for here is to be the value of our reduction factor phi. So let's say that this is to be phi. So let us solve for this. So in order for us to solve for that, we will be using similar triangles. So if you have any methods, if you know any methods other than similar triangles, then you may do so as long as you would be solving for this particular value here. Okay, so what I would be doing is that, well, by similar triangles, I would be drawing a big triangle here. So let's say that this is to be the big triangle. And I would be drawing another smaller triangle here. So let's say that this is to be the smaller triangle. The green na lang. So this is to be the smaller triangle for pretend. Okay, so with that, so erase ko lang itong nasa baba para may space tayo magsulat. Okay, so for your FY guys, this is basically, this is actually 420 as given by the problem. So this is 420. Black natin. So 420. Okay, so once again, similar triangle. So I will be calling this as Y1. This is to be X1. And for the smaller triangle, I will be calling this Y2. And this is to be X2. So for similar triangles, Y1 divided by X1, this should be equal to Y2 divided by X2. So Y2 divided by X2. So substituting known value. So for your Y1, Y1 is equal to 0.9 minus 0.65. So 0.9 minus 0.65. So we will be dividing this by the run. So the run is to be equal to, so what is to be this component? That is to be 1000 megapascal minus 420. So 1000 minus 420. And this is now to be equal to, so where was I again? So Y2. So our Y2 here is to be equal to the value for your phi minus 0.65. So phi minus 0.65 divided by X1, and our X1 is to be equal to 845.126 minus 420. So kung masyado mabilis, paki-replay similar triangles. So 845.126. Okay, so solving for the value for our phi, we would be arriving at an answer of, so for a moment, so phi is equal to, so looking at the calculator to your left, so this is now to be equal to 0.9. So 0.9 minus 0.65 divided by 1000 minus 420 times, oops, I'm sorry, may mali pa dito, 845.126 minus 420. So do not forget about this like I did. So nakalimutan ko lang, pero ratio yan kasi for the value for your X2, that is to be 845.126 minus 420. Okay, so moving forward, so times 845.126 minus 420 plus 0.65. So this is now to be equal to 0.8332. So this is to be the value for your phi. Okay, so, but once again, if let's say for your Fs, it would be more than 1000, it means that your phi is to be equal to 0.9. Okay, so moving forward here, paano ba to? Ano nang gagawin natin? Halimutan ko na. So ito pala, so for the value for your phi mn, so if this is to be your mn, we'll just be writing them here. So this is to be the value for your mn, and this is to be the value for your phi. So for the design strength, phi mn, so phi mn is equal to 0.8332 times 886.3979 kilonewton meter. So with that, our design strength phi mn is now to be equal to, so multiply this by 886.3979, 738.5857 kilonewton meter. Okay, so that is pretty much our answer here. Okay, so reiteration guys, that is to be the solution for case number 2. But for example, once again, that your example or the problem that you are analyzing is to be case 1. So when we say case 1, it means that the value for, your compression block is to be located here only. So kung makikita nyo dito guys, itong red mark na to, ganyan lang. So as you can see, hindi na kayo magdi-divide na to. And for your value for your ACC, so for the value for your ACC for case number 1, that is basically BF times TF only. So take that into consideration guys. And once again, take note that for this example, this is only used. This example is only for positive moments. Because for negative moments, so for example that, let's say for your negative moments, you have, let's say, a T-beam. Kopyahin ko na lang. Mapahiya pa ako ng di oras. Kopyahin ko na lang tong drawing na to. So let's say that this is to be your T-beam. I will just be erasing all. So let's say that this is to be subjected with negative moment. So for example, you are analyzing its design strength for negative moment. So when you say negative moment, it means that the one on top is to be your tension, so tension dito, and the one at the bottom is to be for your compression. And if we are to draw its stress diagram, so let's say that you have your AS here, so this is to be the total area of steel. For your, once again, this is to be for your negative moment, and for its stress diagram, like kung nalilito dun so stress diagram, so ito, your compression block will now be at the bottom part. So, bottom part na lang siya. So, this is to be your 0.85 FC prime. So, 0.85 FC prime times ACC. And this is to be your tensile force. And that is to be ASFS. So, ASFS. Okay. So, ayun lang. And if that is to be the case, guys, you will just analyze this, no? So, rectangular beam lang siya. Because, of course, if this is to be subjected with tension, we are to assume that it is not of importance here. So, with that, guys, so this is to be 0.85 FC prime ABW. So, ganyan lang siya. If, let's say, this is to be your compression block. Okay, and reiteration, that for case 1, so for example, for positive moment, so kunwari positive moment na ulit, and yung AS natin is nasa baba na ulit. So let's say that this is to be the value for your AS at the bottom part already. And let's say that this is to be for your case 1, this is to be your compression area. So for your ACC, that is basically BF times TF. So it would be as simple as that. So parang rectangular beam lang siya. Na ito yung parang kinonsider mo kumbaga. For example. So there. So that is pretty much it for our meeting for today. For our video for today. So I hope you understood. And if not, feel free to message me or better yet, replay the video. Peace.